Hello, everyone, and welcome back to our series on energy modeling fundamentals with Honeybee. And in the previous video, we finally ran an energy simulation of our single family home that we've been building over the previous videos. And we looked at the end use intensity that we got from that energy simulation. But we didn't get to the point of really understanding where this energy simulation data came from and how it was generated. So in this video, we're going to delve into some more of the details of what actually occurred in the energy simulation and make some visualizations to understand this simulation process better. So first thing is first, I'm going to go over to the HP Energy tab and go back over to this result parsing tab here, and you'll see that there are several other components that help us bring in various different results from this SQL result file, which we get out of the energy simulation. So I'm going to grab this component called HB read room energy result and drop this on our canvas. And you'll see this component's much larger and it's made to bring in a lot more of the detailed results that we have from our energy simulation. But it only has a single input, which you can see here is just that SQL file, just that SQLite file. So I'm going to go ahead and connect up our SQL file from our model to OSM component and connect that to the read room energy result. And you'll see the component should run without issues. And if I copy a panel here so that we can actually check what some of these outputs are, you'll see something that if you've gone through our Ladybug tutorial series should look very familiar to you. So we have what we call here a data collection object, and this is specifically an hourly continuous data collection object. And this is essentially a wrapper around a list of data, a list of time series data. You can see specifically there are 800,760 values in this data. And those values correspond to cooling results at each hour of the simulation that ran here. And you can see that we have these data collections for heating, for lighting, for a few of these different end uses. If you are familiar with our Ladybug plugin, you probably already have some gears turning because once you have data in a data collection like this, there's so much that you could do with it. You could, let's say, make a sun path plot using the cooling energy use that you can find out which suns you want to block to mitigate the cooling energy use of your building. Or you can make a windrows with just the values in the heating data collection. So we're not going to do anything too crazy in this video, but we are going to make use of the fact that we have data in these data collections. Maybe first I'll just show you some ways of at least understanding what this data collection is. So I'm going to grab this Ladybug component that's just called LB deconstruct data, and I'm going to drop this onto my canvas here. And you'll see that this can take any of these data collections as input. And if I plug my cooling data in here, for example, you'll see that the data collection is really nothing more than a header, which has a bit of information about the data that it's contained. So this is a data collection of energy values. It's running from the whole year from January 1st to September 31st. And it's for the specific room of our energy model. And it's specifically the total cooling energy of that. So that's what the header tells us. The values on the other end, this is the actual raw list of 8,760 values for the cooling energy use at every single hour of the year. So you could immediately start to process this data with some native Grasshopper components. I mean, as a proof of concept, I could just show you if we were to use the mass addition component, the native Grasshopper mass addition, I can add all these values together and you'll see that this should be the same. Well, I guess this is the same effectively as our cooling energy, right? Our 20.6 kilowatt hours per square meter here multiplied by our gross floor area. Let me just see if I can do this for a second so that you guys can validate this for yourselves. So if I take our EUI end uses, I multiply them by the floor area so that I'm looking at raw kilowatts. We'll see, yes, this should match pretty much perfectly with the mass addition of all the cooling values in there. So this gives you a sense of what we're actually looking at here. We're looking at the hourly cooling values instead of everything aggregated together like this. So, all right, so that gives you a sense of exactly what this data collection is. But of course, it'd be most useful, instead of looking at just a raw list of values, it'd be much more useful if we could visualize this somehow on, let's say, a chart or a plot. So I'm going to delete all of these deconstruct data components and mass addition component there. And I'm going to grab a Ladybug component to visualize data collections. I'm going to grab this LB hourly plot component and drop that onto my canvas. And if I connect up our cooling data stream to the data input of the LB hourly plot, and I go over to our Rhino scene, you should see that we now get a visualization of the hourly cooling energy use in kilowatt hours for each hour of the simulation. So I'm going to go into top view actually to make this a little bit easier to see. And it looks like these results are generally making sense to me. So if I were to ask myself at what time of the year and what time of the day do we have the highest cooling energy use, it would seem from this chart that the biggest cooling energy use is happening sometime around August or September. This is quite a spike. I guess there's a little bit of a heat wave in July as well. But typically, our biggest cooling loads are coming in the afternoon between noon and 6 p.m. We can see these higher values of around almost 6 kilowatt hours we get up to in September in that afternoon period. And this generally would make sense because that tends to be the hottest part of the day. That's when I would expect to have the highest cooling energy use. So I could tell intuitively that the cooling energy in my simulation is being driven by those hot outdoor temperatures in the afternoon, and probably the high sun that you'd also have in the afternoon as well. So let's go and do the same thing for our heating energy. We have a heating data collection here, and I can go and connect that up to the data of the LB hourly plot. And oh, this is interesting. Our biggest heating energy use is happening particularly in the nighttime, it seems, which I guess would make sense because that is the coldest part of the day and you don't have any sun to help you out with offsetting the heating load. And importantly, in the winter, which would make sense in the months of January, February, and December, those seem to be the months with the highest heating load. And altogether, we can actually see if I hold down Shift, I can connect both cooling and heating to the same component and get them both visualizing at the same time. We can do the same thing for lighting. I can hold down Shift to connect up the lighting, and we can get a plot of that. And I can hold down Shift on the electric equipment and connect those up as well. And this is starting to show us some very interesting behavior here. So whereas the heating and cooling we could very clearly see are being driven by outdoor climate factors like how cold it is outside or how sunny it may be, our lighting, for example, that we have here, this is very, very different. It looks very, very different than the others. And I might ask you, what exactly is it that is driving the lighting energy use in the same way that I asked what is driving the heating energy use? And if you guys are smart and remember back to a few videos earlier, you remember that we had schedules, right? There were schedules that we were assigning to our model to make sure that the usage of that space was representative of a residence. Well, that schedule is exactly what is driving the lighting here. And you can see it's meant to kind of mimic, you could understand the daily behavior of the occupants in this idealized residence, that they are turning off the lights at night when they're sleeping, which makes sense, but they may turn them on for a little bit in the morning when the sun isn't quite up yet. But I guess in this particular residence, people are leaving for work or they're not leaving all the lights on in the middle of the day because they're mostly off or they're at a very low value for most of it until people get home, and then the biggest usage of lighting is happening sometime around, looks like between 7 and 9 p.m., I guess when people are making dinner or watching TV. So yeah, so we can already begin to understand some of the assumptions of this and make sure that they are really a good representation of how we expect this space to be used, how we expect this real building to be used. And generally, I think my mother-in-law's house that we're modeling here, I think this fits pretty well with when people turn on the lights. For the equipment, we see something similar, right? That the highest peak in equipment, the equipment schedule is during the evening when people are turning on their kitchens and TVs and doing laundry and lots of other stuff. But we also see that there's a lot of equipment on in the middle of the day. And also importantly, we see that it never really goes down to zero. So this is probably trying to model the fact that we have a lot of electronics these days that are on standby power that never go completely off. Things like our computers may not totally turn off. They might just be in sleep mode, or our cable boxes might never really go off. So we can see why this electric equipment profile would be different than the lighting profile, for example. And I think that's, for the most part, we don't have any gas equipment in this model, any process equipment. We do have hot water, so I can connect that up to here, and we can see the energy uses of hot water. And this is an interesting one. So we see the biggest peak in energy use for our hot water is well in the morning. So if you were to probably intuit what is going on in this case, that's probably because in this model people are showering in the morning. That's probably the biggest usage of hot water that we have. Maybe in the evening they're doing some laundry or something or they're cooking, so that could be another usage of hot water. But it seems like the biggest use of hot water in this case would probably be that shower going on in the morning. So all right, so we get a deeper sense of actually what's going on in this model that we didn't get from just looking at the EUI. Now you'll notice that there are a bunch of other outputs for this component that we aren't getting any data for. And that's not because these data streams don't exist for this model. It's simply because we haven't really requested them. So before we end this video, let's just try and request some other outputs from this simulation so that we can begin to understand it on an even deeper level. And you'll notice under the HB Energy tab, if we go to the Simulate section, there are a whole host of components that help you customize the parameters from the simulation. And one of them is called HB Simulation Output. And this assists you with requesting various different types of outputs from the model. So by default, we don't request all the possible outputs that you could be getting from the simulation. And the main reason why we do that is because Energy Plus actually has hundreds of outputs that you can request. So you can imagine if you did that even for like a single building like this, a single zone building, you'd end up with a huge SQL file, a lot of data that you may not necessarily want hogging up your hard drive. So we have you request the things that you want from the simulation using a component like this HB simulation output. So all of these inputs of this component, almost all of them are made to take a Boolean toggle. So I'm just going to double click the canvas and bring up a Boolean toggle. I'm going to set it to true, and I'm going to connect it to the different types of outputs that I want from the simulation. So I would like zone energy use. That's pretty much what I'm observing right now, and I'm looking at cooling, heating, and lighting, etc. But HVAC energy use, maybe we'll just leave that the way it is for now. I do want these gains and losses because we see some of these other things like people gain, solar gain. These are ones that I could get by actually requesting them. So if I connect up true to gains and losses, I'll be able to get data around that. Comfort metrics, oh, this sounds interesting. Maybe I'll request this one as well so we can get this data out of there. And maybe I'll request this surface energy flow. We'll request these types of outputs. So this is significantly more than the default, which is really just to get the zone energy use. But let me see. In order to actually make sure I've run a simulation where I request all these outputs, we have to somehow connect the simulation output to the simulation parameters of this HB model to OSM. So we need one more component to be able to do this, and that is this HB simulation parameter component here. If I drag and drop this component on the canvas, I can connect this sim output to the output input of the simulation parameter component. I know our naming is maybe getting a little confusing here, but trust me that this is the right way to do it. And so if I do this, I've created essentially a simulation parameter object, which will change the way that our energy simulation is run. And you can see there are a lot of things you can customize about the simulation. You could select a run period if you don't want to run the entire year, for example. Or you can add daylight savings period, you could add holidays, all sorts of things can be customized about the simulation from these parameters. But this is all I want to do right now. I just want to request some different outputs. And maybe I'll make a little bit of room for myself here so that I can easily connect them in without making my definition too messy. Why don't I can even just group these to keep it organized. All right, and if I connect our simulation parameters to our HB model to OSM component, then you'll see the simulation will start running again. Right, it's going to rerun everything. It only took about 15 seconds last time, so we shouldn't be waiting too long here. But importantly, when it's running the simulation this time, it's going to record all of these other types of outputs, like gains and losses and like comfort metrics. And we should be able to see that in the results that we have here. So, okay, so again, our EUI didn't really change, right? It's still the same simulation. We just requested some different outputs. But you can see now we get things like this people gain. So if I go and I connect our people gain from our HB room energy result to our LB hourly plot, you'll see that we can now get a plot of the energy that's being contributed by people to the space. Or I can connect solar gain and see what that looks like. And this is interesting. Okay, so this is not being driven by a schedule like all the other ones, right? This is actually being driven by which windows are seeing the sun at the different hours of the simulation. So hopefully I encourage you guys to go through these outputs and really get an understanding of what's going on under the hood, that we're actually simulating each of these hours of the simulation. And this is how we ultimately end up with aggregated metrics like end use intensity here. So In the next video, we're going to delve even deeper into some other different types of results and not just get an understanding of how the simulation ran, but really why that energy use is the way it is. Why did it end up like this? So thank you guys for making it through this one, and I will see you in the next one.